Okay, so let's have a little look at this right now. So this function, f of x equals the absolute value of x minus 4 plus the absolute value of x minus 5. So let's just first of all maybe have a little look at how we're going to deal with differentiating that function. Okay, so okay, these are admittedly kind of a pain to deal with, but they're also where you see them a lot in math. So how do we do this? Well, an absolute value function, the best way to deal with functions like this, like absolute value functions or other functions like them, are to represent them as piecewise functions. Okay, so let's first of all let's take this one, just the absolute value of x minus 4, and let's write that as a piecewise function. So what are the different behaviors of the absolute value of x minus 4? Okay, so we know in general that the absolute value of a just equals a whenever a is what? Positive. Whenever it's non-negative, I should say, right? Or actually, whenever it's positive. I shouldn't say positive. Whenever a is positive, it is its opposite when negative, right? And it's 0 when 0, right? Okay, so what does a represent? A represent, the fancy word for this is argument. Do you guys get what I mean when I say the argument of a function?
No.
Okay, well I better explain that thing because I've said it a few times. So the argument of a function is always the whatever is inside that function, right? It's the function that's inside the function. So the argument of the absolute value function here is x minus 4, right? It's what the absolute value function sees, okay? So in general, now it could be a function of x like it is here, but in general, whatever it is, call it a, this is always the behavior of an absolute value function, right? So let's apply that to this specific case of an absolute value function where a, the argument, is equal to x minus 4. So we know that the absolute value of hand is equal to hand whenever hand is positive, right? But we could probably write that in a better way, couldn't we?
Probably.
What if we solve that for x, that inequality? Because really, don't we want to solve it for x? We don't want to have it solved for x minus 4. We want to know the values of x where the absolute value function is unchanged. So what are those going to be then? We'll go ahead and trade this for the solution. X is what? X is greater than 4, right? So there's the domain where the absolute value function is unchanged. Okay, where does it equal its opposite? Well, wherever it is less than 0, which is when what? X is less than 4, right. And we know that it equals 0 whenever x minus 4 equals 0, which is just going to be when x equals what?
0.
4. Right? Okay, get the idea?
Yeah.
So there's the absolute value of x minus 4. What about the absolute value of x plus 5? I bet you can now kind of jump right to the answer. That equals x plus 5 whenever x is what? Greater than negative 5, right? Whenever x plus 5 is greater than 0, right? And it's equal to 0 when x equals negative 5, and it equals its opposite whenever x is less than negative 5, right? Okay, so if we wanted to combine those things then, written just a little bit smaller. That's all right. Okay, so now if we want to combine those things, what does the function, well, we don't have to. Okay, right, so here's where we get lost. Okay, so now we've got to differentiate this thing, right? So let's go ahead and calculate, I wish I made this just a little bit smaller. Let's calculate over here the derivative with respect to x of x minus 4. So we're just going to differentiate this piecewise function. Well, what do you suppose you do? Yeah, we just take the derivative of each piece of the piecewise function, right? Okay. So the derivative of x minus 4 is defined as, well, what's the derivative of x minus 4? 1, right? Is 1 whenever x is greater than 4, it's, what's that going to be if I distribute the negative sign and differentiate? Negative 1 whenever x is less than 4. And what's happening at the middle there?
Can't find the derivative.
Can't find the derivative. How come? Because it's a sharp corner, which we could see graphically. We know that absolute value functions are b's, aren't they? Right? Or we don't even have to have a graph, though, because we can see that for every value of x greater than 4, the derivative is positive 1. For every value of x less than 4, it's negative 1. And so there's no way to have a smooth transition at 0, is there? Right? So it's undefined at 0. Right? It's not even, so we could either write it's undefined, or we can just leave that part off. It's probably easier to do. Right? Because that's the complete derivative right there. So notice it's not defined for 4. Just the values above or below 4, right? So same thing down here. What's the derivative with respect to x of the absolute value of x plus 5? Well, it's 1 whenever x is greater than negative 5, right? And it's negative 1 whenever x is less than negative 5. Okay? So then what's our derivative going to be? So if we want to write down the derivative of the whole thing, which this is f of x, so let's just figure out what is f prime of x. Now, what are the intervals where the derivative is going to change? Because look, the derivative of the first term changes at the value x equals 4. The derivative of the second term changes at the value x equals negative 5. Right? So every place where one piece of this derivative changes, you see that the sum is also going to change. Because all we're doing is just adding up these two things. Right? So then what's going to happen, we're going to have to make maybe a little bigger piecewise function here. Maybe we can collapse it a little bit as we move on. But if we're going to go from, let's go from the leftmost boundary to the rightmost boundary. Leftmost boundary is at negative 5, isn't it? Right? So for values of x less than negative 5, what are we going to get? Well, what's the value of the first term when x is less than negative 5? When x is less than negative 5, which part of the domain am I in? The bottom one, right? Because wouldn't you agree that all x values less than negative 5 are certainly less than 4? Right? So we're going to be in this part and that part, right? And we're just adding those two up, aren't we? So what do we get? Negative 1 plus negative 1 is negative 2. Okay, so then we've got to now find the next region, right? So now we have values of x less than negative 5. What's the next part of the domain that we'd have to consider? Yeah, between negative 5 and 4, right? Because now we're going to shift and pick values greater than negative 5, but let's stick with values less than 4, right? So we've got another part of the domain here. X is greater than negative 5 and less than 4. And then we would be where? We'd be oh my gosh, seriously? So then we would be here, right? Greater than -5 and less than 4 means we'd be adding up -1 and +1. So the value of the derivative would be 0. Yeah. Right, so, and then finally, we've got to pick the last part of the domain where things have changed, which would be when x is what? Greater than 4. Okay, good. Okay, and there we're going to get, so we're going to have, we're going to have this guy and this guy, right? So it's going to be 1 plus 1 is 2. Okay? So that's our derivative function. Okay? Make sense? Yep.
I'm sorry, but can you explain again
Why you add them together? Because that's what the function's doing. See, the function's saying we've got f of x is that function plus that function, right?
We didn't really need to do the piecewise functions of the individual absolute values, then, did we? We could have just went straight for the derivative of each function.
Well, meaning if you use, what formula are you using for the derivative?
Well, we did the piecewise of each individual absolute value,
Mhm.
and then we did the derivative of the absolute value.
Right, so what you're suggesting is you could have, and this is what I almost did, we could have just bunched these together and then differentiated, right?
Yeah, or you could just differentiate each one individually, but just not do that first thing where we did the piecewise, right?
Well, okay, so, right, but my recommendation is you always make an absolute value function into a piecewise function to differentiate. Are you using, there's a formula they give you in the book for an absolute value derivative. Is that the one you're using?
No, I never.
So how did you take the derivative of this, for example?
Well, can we do it right here?
We did it right there.
Yeah, that's what I'm talking about.
Mm-hmm.
Yeah, can we
You
just,
skip that middle part.
can we just skip doing the whole absolute value x minus 4 equals, and then the piecewise function?
Well, I mean, I guess, but what I did was I went from, here was the process as it flowed the way I thought about it, the way I do think about it is, so you go from here to here, and then you differentiate each piece to map it onto the pieces of the derivative. Yeah, see what I'm saying? So you can see, I mean, yeah, you're right. I mean, as you do more and more of these, you probably can start skipping some steps. But technically, even if you skip that step, you're still doing it in your head at least, right? Okay, does that make sense? Okay.
Didn't the original problem have like boundaries? Like it had to be between
-9.
Yeah.
It did?
Yeah. Oh, we're not done yet. Okay.
Oh, okay. So, yeah, I guess we got to go back to the original problem, don't we? Okay, so there it is. Okay.
How did we get those in? Sorry.
Okay, so what are the extreme values of the function? Okay, yeah, this is good. So then let's take this function and let's put this on a table, right? So now we've got there's our x-axis. So we've got the x row, we've got f, and we've got f prime. Yep.
I'm not really 100% sure why we even had to do all this derivative stuff if you could have just done it. You could have gotten the same answers and done it a lot simpler.
Okay, what way could you have done it more simply?
You just plug them in. Like if you go to the top, and I saw that like the numbers, I think it's -9 and 9. If you just plug those in, they would give you your extreme values.
Okay, so yeah, you could. I mean, you could just graph the function, and you know, and that's actually, I would say, for a problem like this, you might expect me to say, well, no, you're cheating, but actually, that's not a bad thing to do. Whenever you've got straight linear functions like this piecewise function is composed of straight pieces, it's not curvy, then you can bypass the calculus sometimes. Shh, quiet, please. You can bypass the calculus and maybe just graph the thing. Look at the graph.
Well, because I just like plugged them in. And because the negative 9, if you just plug them in where x is, you do negative 9, 0, and 9, they give you your extreme values.
Okay, but 0 is not.
It's in the middle. That's how you got 9.
Yeah, okay, but see, there is something that maybe you need to consider there. Because you didn't find the critical numbers. And so you lucked out, but you didn't check the critical numbers. So let's look at them on this table here. Right, so we know that our domain is constrained to go, it's a closed interval from negative 9 to 9, right? So we'll go, there's our negative 9, there's our 9. So looking at the derivative now, if we go back, I'll go forward one here, is that right? Forward?
Yes, forward.
Forward, there we go. Where are the critical numbers? Critical numbers are places where the derivative equals 0 or where what? It's undefined. Okay, so we got one at 4 and at negative 5, right? Those are the places where our derivative doesn't exist, right? Those are the places where we knew we had sharp corners and the derivative was undefined, right? Notice that the derivative skips that gap. Skips from values less than 4 to values greater than 4. Skips from values less than negative 5 to values greater than negative 5. So that's how we identify those as critical numbers. Yes?
Would that be like a hole in the function?
Yeah, it would be like a hole in the function, exactly. Okay? So if we go back then, we can add those critical numbers. They were, what was it, negative 5 and 4?
Yeah.
So negative 5 and 4 are places where our first derivative was undefined. So therefore, they're critical numbers. So now all we have to do in this problem is we're just going to compare, we're finding absolute extrema. So what's our strategy? Well, we compare the values of the function at the endpoints to the values of the function at all of the interior critical numbers and just see who wins and who loses, right?
Yeah.
That's it. So we would just plug those back into the original function. Okay? And then just compare. So you're going to be comparing these values. Right?
So one of them doesn't work though, because we only got
Because what?
one of them doesn't work because we got 3. We got 17 now.
Well,
Like a 0 in the middle of each graph?
well, zero's not. We don't need to check 0 because zero's not a critical number. Right? We only have to check these. And let's go ahead and do that. So if I plug in negative 9, what do I get? What's the absolute value of negative 9 minus 4? 13. So f of negative 9 equals 13 plus 4 is 17.
Yes.
So we get 17 there. What's the absolute value, or what's the f of negative 5? 9. Okay. Okay. And f of 4 is 9. Good. And f of 9 is 19. Okay. Is that right?
Yep.
Yeah.
So how come, even though it's at undefined, plugging in?
Because the derivative's undefined. The function's not. Right. Okay. So then these were those guys were tied for the winners, but notice something here about our derivative function. The derivative has a value of 0 in between negative 5 and positive 4. So what does that mean the shape of the curve is? It's a flat curve, isn't it? So if we graph this thing, all the values of the function between negative 5 and 4 are 9, right? So that makes the answer, this is a little bit bizarre then, when we have to answer the question, where are the extreme values? Okay, well the extreme values are 17, 9, and 19, right? Those are the values from line 2 that we're comparing, right? Where does the extreme value of 17 occur at negative 9, x equals negative 9? Where does the extreme value of 9 occur? Well, 9 occurs on that whole interval, doesn't it? The value of the function is always 9 between negative 5 and 4.
How do we know negative 5 goes before 4? When we put it in, what does it
In here, you mean?
Yeah.
Because this is the x-axis, right? So it's gonna act just like a number line.
Okay.
So bigger numbers go to the right. Okay, yes, sir.
So, on like a line that had no slope, would just every point be a streamer?
On a line that had no slope, that wouldn't be a function, and so it wouldn't apply. Because we're only dealing with.
You mean zero slope?
Yeah, zero slope.
Oh, like this one does. Yeah, exactly. Then so those are all those infinite points. The extreme value occurs on all of those infinite points right there. Why is that not working? What's going on?
You ran out of pressure lane.
I think I did. That's weird.
Better call
There it is.
it.
I know. So, right, you get that? So that contains an infinite number of points. And then the extreme value of 19 occurs at x equals 9. Is there another, I saw a hand over here. Okay. Does that make sense?
Yeah.
Okay. So you have to do some interpretation of that problem a little bit. Okay, so moving on. What is this?
Your board looks a little off.
It's,
It's tough for the day.
yeah, it is. Something's not working. Okay, so let's look at another example of the first derivative test. That's the thing I guarantee that you're going to want to have more practice on. So how about if we take new function, different than last time. Let's do a trig function.
Can we do the secant one?
No, but I'll do a different trig function. Yeah. Okay. Okay, so let's find, I just called it our new stuff, meaning we want to find, think about what we talked about earlier this week. We talked about places where we're going to find the intervals where a function's increasing and decreasing, and then the relative extrema, right, by using the first derivative test, okay? So here's our function. Let's find it. So what's the first step probably if we're going to use the first derivative test? Take the derivative. Okay, so let's differentiate. So we've got f prime of x is what? Minus cosine x. Good, right? So I want to find, and remember what my goal is here. I'm going to make a table, and all the first derivative test does is it just gives us an easier way to use the table to determine whether the critical numbers panned out or whether they failed, right? Because the critical numbers are the places we have to check to find the relative extrema, right? Real quick, where do we find critical numbers again? What are the two kinds of places we look? Where the derivative equals 0 and where it's undefined. Okay, so let's start off with the tricky one. Is this derivative undefined anywhere? No, it's not. Because there's no red flags, right? It's a cosine function, which is well behaved, and there's no x's on the bottom, no even root, so we're fine. So none of the weird kind of critical numbers. We just have to find the ones where the first derivative is equal to 0, right? So we got to answer the question, this equals 0 when cosine x equals 1/2, right? Everybody agree? Our first derivative function equals 0 when cosine x equals 1/2. Okay, that's a unit circle.
Negative cosine x.
No, because I was like.
Well, because I'm setting it equal to 0, so I'll just add the cosine x to the other
Oh, yeah,
side.
never mind, that'd be negative cosine x.
Okay, so that's just a unit circle issue. So on our domain, and look at our domain is essentially one lap of the unit circle, right?
Wait, can I do that? I know.
You got your left hand, that's right? You guys know the trick? So try it. So where is the cosine of x equal to 1/2? Do you remember how to do that?
Okay, so,
Well, I don't know how to find this one.
so we put down
One.
two.
Can we just go over it for
So you're gonna wanna have,
So it's a pi over.
But-
Then you're gonna wanna have one.
Oh, is it gonna be this?
remember, so you got
Can we go over it?
the left-hand rule?
Yes.
Okay, so the left-hand rule, here's the left-hand rule, as I remember it. You tell me if I got it wrong.
This is.
So,
The beginning of
right, so here's the x-axis, there's the y-axis, right? Okay? So now you're going to, whichever, we got these three possibilities in between, right? And whichever one you're taking, you're gonna close that finger and you're gonna count the number of fingers to the right. And that's the number that's gonna be divided by 2, right?
Whichever one you're thinking.
Okay, so for example, if we pick this one right here, then the coordinates are going to be, it's gonna be 1, 2, 3, the square root of 4 over 2, right? So the coordinates right here would be the square root of 4 over 2, which is 2 over 2, which is 1, and then 0 over 2, which is 0, right? So if we move up to the next one, this guy right here, well, I close that finger, right?
What degree is that?
So that's gonna, well, you have to fill that in, right? So what are the degrees gonna be for those three?
30, 30, 45, 60.
Right? Or in terms of pi, it'd be pi over 6, pi over 4, pi over 3, right? Okay? And then pi over 2. So we want the one, we're looking for the one where the cosine, which is the x or y coordinate, you gotta remember that.
Cosine is
X, good. So we want the x coordinate to be 1/2, right? So we want the first coordinate to be 1/2. So doesn't that mean that's gonna have to be that finger?
Yeah.
Because now, if I write the coordinates of this finger, it's gonna be, the x coordinate's gonna be the square root of 1, which is 1 over 2, and the y coordinate's gonna be the square root of 3 over 2, right?
Yeah.
That is pretty cool.
It is awesome.
I do like that. Okay, so we just figured it out. So it's 60 degrees, which is what in radians? Pi over 3. Okay. So can I erase this?
Yeah.
Sure.
That's a really good hand though.
That was a pretty good hand, wasn't it?
Oh, it's fine.
I think the last time I traced my hand was many, many years ago.
Did you make a turkey with it?
Eighth grade doing
Yeah.
was turkey.
Exactly.
Turkey.
Okay, so that's going to occur. Okay, so if we solve this trig equation, we know cosine x equals 1/2 when x equals pi over 3 on our interval at least, right?
Yeah.
There's an infinite number of places every, right, it would work at lots of places. It would work there, and it would work there also, wouldn't it? Right, so we got 2 places. So we got pi over 3, where we got an x coordinate of 1/2,
Would you just get naked?
and then if I reflect that down here, I'm gonna get 1/2 negative square root of 3 over 2, right? So I got x equals pi thirds, and x equals, what's that gonna be? 5 pi thirds, it's 2 pi minus pi thirds, right?
Yeah.
Could you also use just negative sign?
Well, okay, but no, because look at my domain. My domain is from 0 to positive 2 pi, right? So we can make our table now. Agreed?
All the way around.
Those are our 2 critical numbers, right? So now our table.
How did we get that?
Is there 2 pi over 2?
Yeah.
6 pi over 3. And then you just take pi over 3 away.
Okay, so now watch, this is a little different than what we did last time. Watch carefully. So when we want to write the domain up here, watch how I'm going to write this. I'm going to write rounded brackets, which means not included, right? Open interval from 0 to 2 pi. And then our critical numbers were pi thirds and 5 pi thirds. And I can show that they're critical numbers because what goes in this row? 0. In the derivative row, we get 0, right? Okay, so now all we got to do to apply the first derivative test is we've just got to pick some test points,
Yep.
right? We got to pick test points. Now, I didn't really emphasize this last time, so kind of ran out of time, but we got to be careful in picking our test points. When I want to test the behavior using the first derivative test of the critical number pi thirds, I have to choose one to the left and one to the right. So somebody pick out a good value to the left. Pi over 6. Okay, so we'll pick pi over 6. Because I want to pick a value between my endpoint, because the endpoint's not included, right? And pi thirds. Now, what's going to be a good endpoint or a good test point to the right of pi thirds?
Over 4. 2 pi.
Oh, just kidding.
Okay, could I pick, for my other test point, I'll throw one out there. Could I pick
2 pi over
11 6 pi?
Or you could put 2 pi.
No. Yes, you could. No, I
Oh, we're
got
talking about that point. I thought we were talking
I
about.
thought you were
I thought we were
talking
talking
Okay,
about pi over
we
two,
are,
though.
we are. So is this test point going to work for this critical
No.
number?
So, we-
Okay, how come? You're right.
Because it's,
Yeah,
it's past pi.
Ah, okay.
Pi
they
over
already
3.
changed the rest.
Okay, very good. Because now let's talk about why that is. Because this test point is on the other side of the next critical number, and the behavior can change there, right? So the fact that what if hypothetically this was positive, does that mean that the function is necessarily increasing in there? No, right? It doesn't. So we have to pick critical numbers between all of the critical numbers. So probably an easy one would be just pi, right?
Yep.
So now,
Right in between.
so now we just want to find, do we need to go through and actually evaluate the whole first derivative and get number values?
No.
Just need signs, so it makes it easy. Right, so our derivative function is just 1/2 minus cosine x. Whoops,
Yes, it is.
what is my thing doing?
Oh, you need to calculate.
I think it's its birthday today.
It must be, must be.
It's just,
It's its off day.
Okay, so tell me then, what is the, okay, so the sign of our first derivative, so f prime of pi over 6, 1/2 minus the cosine of pi over 6. Now look at the unit circle. Pi over 6 is
positive.
right here, right? That's going to be a big x value, isn't it? Right, so 1/2 minus a big x value, square root of 3 over 2, is negative, right? So that's negative. What about at pi? At pi, the cosine of that is -1, right? So 1/2 minus -1 is positive or negative? It's positive. Okay. Oops, got him on the wrong line. What am I doing? And then what about 11/6 pi? 11/6 pi, that's going to be the same value, if I drawn this correctly, that's going to be the same x value as pi over 6, right? That's big and positive.
So it's negative.
So 1/2 minus big positive is negative. And so now we can draw this picture. If it's going from decreasing to increasing, what does that make? A peak or a valley? No, going left to right, it's got to be a valley, right? Because
oh, that makes sense.
don't get in the habit, this is easy to do, don't get in the habit of going right to left. You always have to go left to right when you're applying these tests. So an increasing function going from left to right is uphill, right? Decreasing from left to right is downhill. So this means you're transitioning from a downhill slope to an uphill slope, right? And so it is a rounded, that's supposed to be a tangent line, it's a rounded valley because it had a zero derivative, so it's not sharp. And it's a transition from negative to positive. Here we're going from increasing slope to decreasing slope smoothly, so it looks like that. And we got it. So what's
our answer?
that represents our whole answer.
But is it like pi over 3?
So what was the question asking on this one? We wanted to know,
Good question.
well, I didn't ask a question, I just wanted new stuff. So I probably you're gonna get asked, what are the extreme, well, what are the points where you get extreme values? So what are the points where you get relative extreme?
Pi over 3.
So it's gonna be at x equals pi over 3 and y equals, well, whatever I get when I plug pi over 3 into my original function.
So you still have to plug it in.
You still would have to plug it in, right? So you'd plug it in there and we'd get that answer, and whatever that is,
Sine pi over
right? Okay? We'd get a relative, that's a minimum, right? We'd get a relative maximum at x equals 5 pi over 3, and we could find the value of the function by just plugging in 5/3 pi. Okay?
I'm so confused on what the new stuff is.
The new stuff just meant this. New stuff meant
Okay.
the stuff that we found, that's just the stuff we found on Monday. That's the relative extrema, which we just found. And then the other part is the intervals on which the function is increasing and decreasing. So tell me, Hunter, on what interval, on our domain, on what interval is our function increasing when x is? Okay, but I want the whole interval. When x is what?
Oh, so like, pi over 3 is less than x, but, or greater than x, but less than.
Okay, so remember, when you're doing a compound, when you're doing an and inequality, you always start with the angle. So x is greater than pi thirds and less than 5/3 pi, right? Everybody see that?
Greater than pi thirds, less than.
But if you're putting that in the computer, it's just like 5 over 3.
Right, so if you're using interval notation, we'd have, how would that look? So if we want to do interval notation, we would say
I give up.
f is increasing on
And decrease.
that interval, right? Okay? When x is greater than pi thirds and less than 5/3 pi. It's going to be decreasing on,
Negative infinity.
well, okay, no, but we're bounded, right?
0.
So 0 to pi thirds. So x is greater than 0 and less than pi thirds, or x is good. Greater than 5/3 pi, less than 2 pi.
Special symbol like with the upside down U.
So the or, yeah, so I can't remember on Math Excel if it wants that or if it wants a comma, but technically this is and this is or. Those
What are the
symbols.
U's? What are the U's then?
Or, okay, those are unions, those are, and when you're talking about a logic statement, these mean and or. If you're talking about set theory, you'd say this means intersection. So the intersection of set, or excuse me, the union of sets is all the stuff combined, right? And, no, that's intersection, sorry. And this is union. Intersection is just the parts that overlap. Union is all of it combined.